Sometimes we need to increase the hydraulic pressure in a system. We can do this by using a device called an intensifier. Basically, an intensifier is a big hydraulic cylinder and a small hydraulic cylinder whose pistons are connected together with a piston rod. To show how it works, let's apply an initial hydraulic pressure of 500 pounds per square inch against this large piston, which has an area of 20 square inches. This gives us 20 times 500, or 10,000 pounds of force, which is transmitted through the rod to the smaller piston at the other end. The 10,000-pound force is now being applied across only 5 square inches of surface, creating a pressure here of 2,000 pounds per square inch. So our initial 500 psi pressure has been intensified to 2,000 psi at this end. Up to this point in our examples, we've used a force on a movable piston to generate our pressure. This device is called an accumulator. An accumulator stores hydraulic pressure as potential energy. This stored pressure can be turned into working energy, that is, flow and pressure. One of the drawbacks when using an accumulator is that it has a specific capacity. Once its fluid is used up, the work stops. To get around this, we need a way to provide a continuous flow. The device we use to do this is called a positive displacement pump. It has a plunger encased in a housing. The plunger is connected to a source of power, usually an electric motor, which moves it back and forth. There are valves connected at both the inlet and outlet ports, which allow flow in only one direction at a time as the plunger moves. When it moves in this direction, the volume inside the chamber increases. The inlet valve opens and fluid from a reservoir is pulled in, filling the chamber. When the plunger reverses direction, the inlet valve closes, and then as the volume in the chamber begins to decrease, the outlet valve opens, allowing the plunger to force the fluid out into the system. As the plunger cycles in and out, an intermittent or pulsating flow is produced. Although reciprocating plunger pumps have a place in industry, usually in very high pressure applications, a more commonly used positive displacement type pump is the rotary pump. It's basically a housing with inlet and outlet ports and a rotating group which develops a smoother fluid flow and pressure. One style is the vane pump. In its simplest form, it looks like this. The rotating group consists of a rotor and movable vanes. The rotor is offset to one side of the housing, and the vanes are free to move in and out. When the rotor is turned, the vanes are thrown outward by centrifugal force, forming a positive seal here. The increasing volume here on the inlet side allows liquid to fill this area, while the decreasing volume on the outlet side here forces the liquid out into the system. In a hydraulic system, there is a direct relationship between pressure and resistance. How much pressure a pump develops depends on how much resistance it encounters. This resistance basically comes from two sources: the object's resistance to being moved and the fluid itself. If there were no fluid resistance, the pump would only have to generate enough pressure to overcome the object's inertia and friction. However, since fluid resistance is always present in a hydraulic system, the pump has to produce more pressure to overcome it. Notice that the gauges indicate highest pressure here, close to the pump, and decreasing pressure here, here, and here, the farther we go along the system away from the pump. Since energy cannot be destroyed but can change form, this loss of pressure shows up as heat. It is caused by the friction of the molecules of the fluid rubbing against each other and the walls of the system piping. Hydraulic systems can be designed to reduce heat generation by minimizing the number of bends in the line and by using the proper size tubing. Altering the size of the tubing can affect both the flow rate and the velocity of the fluid in the system. Flow rate is the amount or volume of fluid which moves through the system. It is usually measured in gallons per minute, or GPM. Velocity is the speed of the fluid as it moves through the system, usually measured in feet per second. Increasing either the flow rate or the velocity will increase the friction, and therefore the heat which the system generates. The relationship between flow rate and velocity can be shown with these two pipes. If we want the fluid to move through both pipes at a flow rate of 5 gallons per minute, the fluid moving through the smaller pipe will have to move faster than the fluid in the larger pipe. The additional friction caused by the faster moving fluid will create more heat. Another factor that influences the efficiency of a hydraulic system is the hydraulic fluid that's used. In our next lesson, entitled Hydraulic Fluids, we'll take a close look at the various characteristics of hydraulic fluids and the effect they can have on hydraulic systems.